Today we are going to look into graphing complex numbers and what that's going to mean when we look at both a real and imaginary component. So our introduction says, if the number line is filled with real numbers, how can imaginary and complex numbers be represented geometrically? So graphing. In this lesson, we are going to learn a way to graph complex numbers, which, as a reminder, complex numbers, remember, have the real component. Whoa, what happened there? A plus the imaginary component, which we write as BI, where A and B are numbers. Okay, and we are going to kind of interpret what the graphical meaning of these complex solutions are going to be. So 97 says AV and Tran were trying to figure out how they could represent complex numbers geometrically. AV decided to make a number line horizontal, like the x-axis, to represent the real component. So the x-axis in the complex number system represents the real component, okay, which is the A of our complex number. And then a vertical line, like the y-axis, to represent the imaginary component. So the imaginary part of the number is going to be plotted vertically. So that is our B value, okay? So it says label the axes at right like AV described. So once again, can't stress enough that the real component of a complex number goes on the x-axis, and then the imaginary component of the same complex number will be the y value that we'll plot. So the question asks on B, how could AV and Tran graph a point to represent the complex number 3 plus 4i? Okay, well, let's think about it. What we are going to do is we are going to start at the origin. So we are going to move from the origin. And what are we going to do? Well, let's look at first the real component. So we are going to move 3 horizontally. So 3 to the right because it's positive 3. If it's negative 3, we'd move to the left. And then 4 is going to be the vertical component, so in this case it's positive, so up 4. So it's just like plotting the point 3, 4. So this is what we're thinking in our head, 3, 4. But in this case, what is 3, 4 going to represent? The complex number 3 plus 4i. Okay? So let's go ahead and graph that. Maybe I need to make my pen a little thicker now. So we have 3 plus 4i, so over 3, up 4. So this point right here is representing 3 plus 4i. Okay, so then now what we're going to do on C is we're going to just practice plotting points, and you're probably going to catch on relatively quickly, so go ahead and you can pause me and try some on your own when you feel confident. So on letter I, the first one, we're doing 2 plus 5i, so really we're plotting 2, 5. So over 2 on the real axis, up 5 on the imaginary axis. So this purple point right here represents 2 plus 5i. All right, so now let's go ahead and do number 2, which is 6 minus I. So what can this be written as? This can be written as 6 minus 1i. So what are we plotting? 6, negative 1. So over 6, down 1. So this point below the x-axis, or what we'd usually consider the x-axis, is going to be 6 minus I. That represents that complex number. Okay, now let's go ahead and look at number 3, negative 5 minus 3i. So negative 5 is the real component. Go back 5 and then down because it's negative 3. So we're in that third quadrant, and that's going to represent negative 5 minus 3i. All right, so now on 4, what do we not have? We don't have an imaginary component. So this can be written, any real number can be written as a complex number by just tacking a 0 in front of I, because what happens when we multiply by 0? It really makes the term go away. So if I'm plotting the real component, look what happens. It ends up on the real number line. Okay, so any real number is not going to move from the x-axis because it's already represented with our normal everyday number line. So this is the value 4. Okay, now how about this next one? In contrast, on number 5, we have 7i. How can we write this as a complex number? 0 is the real component. There is no real component. So where is that going to go? That is going to go on the imaginary axis, the y-axis. So 1, 2, 3, 4, 5, 6, 7. So this point on the imaginary axis is just simply the pure imaginary component, so 7i. And then on the final point, we have negative 4 plus 2i, so we have imaginary and real components, so negative 4, 1, 2, 3, 4, and then up 2. So this red point represents negative 4 plus 2i. So hopefully you've kind of mastered or feel more comfortable with plotting complex numbers. Now we're going to call this kind of just the complex set of axes. On this next problem now, we're going to think about why might we ever use complex axes. So on this new set of axes on 98, we are going to locate the points that are representing all of the following complex numbers. Okay, so we have a lot of points to plot, and it's very important that we plot them correctly to notice a pattern that's going to be happening. Okay, so you can pause me and go ahead and plot all 4 points on A. So we're going to do 3 plus 4i. Again, this is the real, this is the imaginary, and we're focusing on plotting our points. So we have 3 plus 4i over 3 up 4. I'm going to make my pen a little thicker maybe. Okay, and then we have over 3 down 4. Then we have back 3 up 4. So I see some conjugates going on here. And then we have back 3 down 4. Okay, so A, I graphed in purple. So now on B, how many complex numbers are represented by this statement? 4 complex numbers. So we have to graph 4 plus 3i. We have to graph 4 minus 3i. And then we have to consider the negative case of 4 because of the plus or minus out front of the first component. So we have negative 4 plus 3i, and then we have negative 4 minus 3i. So that makes 4 cases out of this expression. So we have over 4, and then we have, over 4 up 3, and then we have over 4 down 3, then we have back 4 up 3, and then we have back 4 down 3, okay, and we can see a lot of symmetry going on. So now in, let's see, not purple, in green, we're going to go ahead and graph C, which starts with 5. Where do real numbers go? On the real number line. So we go over 5 and up 0 because we don't have an imaginary component. And then we're going to graph negative 5, so that's going to be the mirror image in the backwards direction. And then what do we have? 5i. So we have 0 real component, and then up 5 on the imaginary number line. And then we have down 5 for negative 5. What do you notice about the graph? Hopefully, if you graphed everything correctly, okay, we can notice that it looks like a circle. In fact, maybe I can get really fancy. Maybe I'm going to regret this and do my circular shape here. Let's see what happens. I'm going to start in the middle. Oh no. Delete. One more try and then I'll be done. Okay, we have that circular shape going on. This could be a lost cause. There we go. Okay. What do you notice about the graph? Let's go ahead and write our response. It looks like a circle. It looks like a circle, and then the second question asks, how far is 0, 0 from each point? Well, the easiest to measure from the origin is straight up, straight down, straight left, straight right, because we have to use another geometric idea to measure diagonal lines. But if we look, okay, what is the distances from the origin on the axes? It is 5 units. So what do we call the distance from the origin to a point on the circle? The radius of the circle is 5. Now look very carefully back at these numbers that we graphed, 3, 4, 5. If you think deep into your geometric knowledge bank, the 3, 4, 5 right triangle was something that occurred a bunch in geometry. So we're going to look further about that in the next questions. So on 99, it says, on the real number line, okay, so we're just talking about real numbers for a second, the distance from 0 to a point on the line is defined as the absolute value of the number. We worked a lot with that in Algebra 1. So now in Algebra 2, we're going to look at, in the complex plane, which is what we just worked on the first page of our notes, the absolute value of a complex number is not the distance from 0 on the real component, it's the distance from 0 on the real and complex or imaginary components of a complex number. So in order to measure absolute value of complex numbers, we have to use a two-dimensional system, which is the XY axes. So in the previous problem, the absolute value of all the complex numbers was 5, because if we go back to our picture, okay, what is the absolute value going to be? It's going to be the distance from the origin to each point on the circle. Okay, so the length of all those blue lines that I just drew in is 5. So the question is, how are we going to figure that out when we don't just have points that are on the real or the imaginary number lines? So let's go ahead and see what we can use. What is the absolute value, it's asking on A, of -8 plus 6i? Well, let's graph that first. So we have 1, 2, 3, 4, whoops, I'm going backwards. 1, 2, 3, 4, 5, 6, 7, 8. Of course, it's not going to fit, okay? And then we go up 6. 1, 2, 3, 4, 5, 6. So it's going to be about right here. How are we going to find the absolute value of that number? Well, we are going to have to think about the length that occurs when we draw in the line that goes from the origin to the point, the complex number. Okay, let's make that look a little nicer there. So how are we going to find the length? Well, let's use our geometric knowledge and think about right triangles. Okay, so we have to think about going over and going up. So here's my right triangle. This distance is 8. This distance is 6. So what do we do to solve for this distance right here? We have to use Pythagorean theorem. So to find the absolute value of a complex number, you have to use Pythagorean theorem by taking the real component and squaring it, and then adding it to the imaginary component and squaring it, and that will give us the absolute value, which I'm going to just call x squared. Pythagorean theorem, okay? So when we do this, we get 64 plus 36 equals x squared. And you solve from there. We're all masters at the Pythagorean theorem. 100 equals x squared. What do we do to both sides? We square root to undo. So we get x equals 10, which isn't shocking because 6, 8, 10, okay, is a multiple of the Pythagorean theorem, 3, 4, 5. So try this next one. What is the absolute value of 7 minus 2i? Well, if we picture that plotted, we'd go over 7 and then we'd go down 2. So we'd be right here. If we draw in our hypotenuse and think about the right triangle, we have 7 and 2. So we are going to take 7 squared plus, and remember, whenever you square a negative number, you get a positive. Negative 2 squared equals x squared. So we have 49 plus 4 equals x squared. So what are we looking at? 53 equals x squared. And when we do this, we square root both sides, so we get the absolute value of the complex number 7 minus 2i is the square root of 53. Okay. So now on C, you think, oh no, that's a new problem. But look what they did. They replaced the words absolute value with the absolute value symbol. So what are we really doing here? We're finding the absolute value of 4 plus 1i. When there's not a number there, it's 1. So we have 4 squared plus 1 squared equals x squared. So we have 16 plus 1 equals x squared. So 17 is x squared. Square root both sides. We get x equals the square root of 17. And then finally, in conclusion, in general, we're going to generalize now. How do we find the absolute value of a complex number? Well, we are going to take the real component A and we're going to square it. We're going to take the imaginary component B and we're going to square it. And that is going to give us the absolute value squared. So after we take a squared and b squared and add them together, how do we undo a square? We have to take the square root. So if you look up, how do I find the absolute value of a complex number? This is what it's going to show you. We would have to square root the sum of a squared and b squared. This is the key idea. Whoop. Key idea. Okay, so that is kind of the first big concept of section 8.2.3. Absolute value of complex numbers and how to graph complex numbers. So now the second component is going back to looking at roots of polynomial functions, and now we're going to kind of consider those real roots that we did in section 1 of chapter 8 along with the complex roots that we did in section 2 of chapter 8. So it says on 100, based on the following graphs, how many real roots does each polynomial have? Okay, now real roots are what? Those are the x-intercepts that we can see on the graph. So when we look at graph A, this is not a trick question. You're literally looking at how many times does the graph touch or cross the x-axis. So graph A has 2 real roots. This is just kind of like a matter of vocab and reading very carefully. The word real is important. So then when we look at the next problem, I see 1, I see 2, I see 3. So how many real roots do we have? We have 3 real roots. Okay, that's not too painful. So then this next part says graphs A and B have both been vertically shifted to create graphs C and D. Now, when you look at these graphs, how many real roots does each polynomial have? Well, on polynomial C, does this parabola ever cross the x-axis? The answer is no. So there are 0 real roots. And then if we look at this odd degree polynomial, because we see that they have opposite end behaviors, how many times is it crossing the x-axis? Well, we can see it's only going to cross the x-axis 1 time. So this polynomial has 1 real root. So the polynomials in part C and D do not have fewer roots. What word is missing here? They didn't say real roots, they just said fewer roots. Polynomial C still has 2 roots, but now the roots are not real, the roots are complex. Polynomial D still has 3 roots, but 2 are complex and 1 is real. Very interesting. Okay, so now we have 2 types of roots. So on 101, it says recall that a polynomial function, this is from section 1, with a degree n crosses the x-axis at most n times. For instance, if we look at the quadratic y equals x plus 1 quantity squared, that is going to intersect the x-axis once. So that is this graph right here. If we look at x squared plus 1, that's a shift up 1 unit. It does not cross at all. But then if we look at x squared minus 1, which is a shift down 1 unit, it's going to cross 2 times or twice. Okay, these graphs are shown to you below. So what we're going to do is we're going to consider an odd degree polynomial and see kind of what the case could be. So we're told to sketch a graph of a third degree. So we're thinking of that parent function that looks like a cubic graph that might intersect once, twice, or 3 times. Make a sketch of all of these 3 possibilities. Okay, so first let's focus on 1 time. So if I draw a cubic graph that only crosses the x-axis once, I'm going to keep my normal end behavior, but think, okay, I cannot droop down and cross after I've crossed it 1 time to begin with. So this has 1 real root. Now, if we want 2 real roots, what can we do? Boom, boom, whoops. Can't do that. I just crossed a 3rd time, so let's try that again. What are we going to have to do? We're going to have to just kiss the x-axis. So now we see that we have 2 real roots. And then finally, our 3rd degree, we're going to cross 3 times. So we have 3 real roots. So the main question is, can a 3rd degree equation have 0 real roots? Because we saw up here that it's possible for a parabola, a quadratic, or a quartic, which is the 4th degree, to have 0 real roots. But if we look at an odd degree, which this is odd degree, can it have 0 real roots? Well, what do we know about our end behavior? I kind of mentioned that earlier. Our end behavior on odd degree is opposite. Okay, so if we have one of our 2 ends going down forever or going up forever, then it's inevitable that you're going to eventually have to cross the x-axis. So the answer, I'm going to go ahead and type this one in. It gets a little bit long-winded. Okay, let's see. So can a 3rd degree equation have 0 real roots? Well, our answer in explanation is a 3rd degree polynomial is odd. Let's see. So the end behavior is opposite. We got really good with that in the first section. Thus, the graph will always cross the x-axis. Whoops, didn't know I was typing in all caps. Oops, oh well. The x-axis at least once. Okay, so the moral of the story is that if you have odd degree polynomials, they will at least have 1 real root. If you have even degree polynomials, they may not have any real roots. So our final questions are going to have us algebraically consider some polynomial functions. Okay, now right off the bat, we see that we're considering a odd degree polynomial. So how many real roots could this have? Our answer should not be 0 because we just saw above that we have to have at least 1. So we're going to have 1, 2, or 3, because remember, you can't have any more than the degree of the polynomial. So this is a third degree. Keep that in mind. Okay, now check to verify that x cubed minus 3x squared plus 3x minus 2 is indeed this factored form. Well, we don't know how to necessarily factor cubics when we have a constant at the end. So if I'm going to be verifying, then the only approach I have is double distributing. So what is it? What do I get? I get x cubed, and then I get minus x squared plus x, and then distribute the negative 2x squared plus 2x minus 2. So I get x cubed and then minus 3x squared and plus 3x minus 2, and that is what they started with in standard form. So we can say check. So now what we want to do is find all roots, all solutions when we solve. Now, I don't want to solve in standard form, and we don't have any fancy formula for cubics, so we are going to use the ZPP of factored form. So we're using the factored form they provided. So we have x minus 2 equals 0, and then we have to consider x squared minus x plus 1 equals 0. So this first one solves quite nicely. We add 2 to both sides, so we get x equals 2. So we see that this is definitely a real root. There is no imaginary component. But now when I solve this factor, it's still quadratic. So now when we're using ZPP, we have to still use a formula within a formula. Okay, so we have, let's see, x equals the opposite of b. I'm going to use quadratic formula to figure out what x equals in this. You could try to factor. I'm going to tell you, doesn't factor. So x equals the opposite of b, so 1 plus or minus the square root of negative 1 squared minus 4 times 1 times 1 all over 2 times a is 1. So we have x equals, and when you simplify, you get 1 plus or minus, 1 squared is 1, and then 1 minus 4, so square root of negative 3 over 2. Okay, now, what's the square root of negative 3? It is 1 plus or minus I root 3, because 3 is not a perfect square number, over 2. So these are the two other roots, but they are complex. Okay, so these are complex roots. So would those be seen on a graph, on a normal graph? No. Okay, so how many roots are there? There are 3 roots, 3 solutions. Those words can be used interchangeably when our equation is set equal to 0. So there are 3 solutions, 1 real solution, 2 complex. With that being said, I already kind of jumped ahead, but the final question of the note sheet for this week is, how many x-intercepts does this equation have? Okay, well, to find x-intercepts, what do we always do? We always set y equal to 0, which that's what this question did. Okay, so when we set y equal to 0, we replaced y with 0 and we solved. Okay, what happened? Well, we got, so when we solved, we got 1 real solution and we got 2 complex solutions or complex roots. So what does that mean? When we're asked how many x-intercepts, how many times the graph crosses the x-axis, we look at how many real solutions there are. So that means that there is going to be 1 x-intercept. Okay, now I know this was a lot, but this is just really forcing us to start to sift through major ideas, bring them together, and know our vocabulary. Okay, solutions and roots now are going to usually mean the same thing because most of the time we're solving an equation that is set equal to 0. All right, so great job with 823. We learned about graphing complex numbers, absolute value of complex numbers, and looking at the difference between real and complex solutions to equations. That was a lot. Keep up the hard work. We're almost done, almost to summer, and talk to you later.